Hello, my name is Alejandra Crespo. I study electrical mechanical engineering. My topic is about interfacing with motor sensors called ADC drivers. We examined how in a motor embedded application a developer should create an interface that decodes the low-level driver implementation details from the application code. This interface provides an architecture abstraction that increases the scalability and portability for the application code by making it less dependent on their hardware. I present videos about the topic.
Hi! In this video we'll look at the differential measurement feature of the AVR ADC, when to use it and how it can be used to calibrate the ADC. In normal single-ended mode, only one pin is used for the ADC measurement. The resulting ADC conversion value will reflect the signal applied relative to the device's ground value. This means that a signal will always be measured somewhere between ground and the ADC reference. In some cases, this whole range may not be needed. When using the differential inputs of the ADC, the full resolution can be focused on the area of interest. This means the ADC conversion value will reflect the signal applied relative to the negative input instead of ground. The lower limit of the range will be the negative input, and the upper limit of the range will be the sum of the negative input plus the reference. This setup will therefore utilize the ADC's resolution as much as possible for the expected signal. Let's say that you want to measure a signal over a resistor, where one side is always 3 volts, and the other side is between 3 and 5 volts. If you use a single-ended measurement with a 5-volt reference, the ADC will cover the unneeded range between 0 and 3 volts, decreasing the effective resolution in the area of interest between 3 and 5 volts. If you use a differential measurement, the negative input can be set to 3 volts, and using a 2-volt reference will enable the entire resolution of the ADC to be used between 3 and 5 volts. Another application of the differential mode is to calibrate the ADC offset. By letting the negative and positive inputs of the ADC be set to the same pin, you ensure that the same signal is applied to both sides, and the resulting conversion should read as 0. Any deviation from 0 is caused by offset error. In the linked example, the ADC is configured to perform a differential measurement on ADC pin 0, so the result will give the offset error.
Now we are going to start to look at several different ways that a developer can implement an ADC driver based on the design techniques for microcontrollers. Technique 1. The polar driver. The first technique and the most fundamental is to develop a driver that both the variable or external device to see if it's ready to either send or receive information. For example, an analog to digital converter ADC driver might start a conversion sequence and then simply block the processor execution and constantly check the ADC complete flag. This code will look something like the following. Technique 2. Interrupt driving drivers. Using interrupts in a driver is fantastic because it can dramatically improve the cost, execution efficiency instead of checking constantly for whether it is time to do something. An interrupt tells the processor that the driver is now ready and we jump to handle the interrupt. The use of interrupts can introduce the need to follow a whole additional set of best practices. For example, it's good practice to keep the interrupts short, declare shared variables as bootable, and handle highly priority items and the offload to the application for processing. 23 DMA driven drivers. There are some drivers that move a large amount of data through the system, such as I2S and SDIO. The idea behind these drivers is that the DMA controller can move data around the microcontroller in the following peripheral to memory, memory to memory, and memory to peripheral.
With thousands of amplifiers on the market, how do you choose the right driver amplifier to support your A to D converter's resolution, acquisition time, and system power budget? A good way to start your search for the right ADC driver amp is to use Analog Devices' new ADC Driver Selection Guide for SAR ADCs. One side of the guide shows single-ended input applications, and the other side shows differential input applications. There are 25 SAR ADCs listed on the guide that are currently the most popular choices for new designs. Each of these SAR ADCs is matched up with driver amps based on input signal frequency, supply current, supply voltage, and bias current. This guide was developed by Analog Devices applications engineers who have years of experience in matching amplifiers with ADCs for specific applications. At the bottom left of each side is a listing of the available circuit notes, including actual lab test data for many ADC and amplifier combinations. Copies of the ADC Driver Selection Guide can be easily printed out in PDF format by going to analog.com/ADC drivers and clicking on the blue button titled Download PDF Copy. Be sure to bookmark the ADC Driver webpage, where you'll also find ADC driver-related tutorials, technical articles, recorded webcasts, and design simulation tools. You can also visit the ADC driver community on ADI's Engineer Zone, where you'll find answers to your technical questions by searching or browsing this community. Share your expertise with others by answering questions, or if you have a question, start a discussion. For more information, please visit Analog.
To block or not to block. When developing any driver for a microcontroller, a developer has to decide whether their driver will be blocking or not blocking. A blocking driver essentially stays called exclusion until the driver has completed its stage. For example, the typical implementation for print that is mapped to a URL is blocking. When you make a collide, a no-blocking driver is one that no stall program execution while the driver is complexing its text. For example, print and the URL driver from the previous example could be converted so that it does not block any data load the application to continue execution while it byte is transmitted at the URL. Embedded ADC driver. An embedded ADC driver overview. There are several ways that we could organize an ADC driver, but the way that I like to organize them requires three components: the low-level driver, the application code, and a configuration module.
Analog Devices ADAC 7980 and ADAC 7988 are easy-to-use 16-bit ADC micromodule data acquisition systems sampling at up to 1 megasamples per second. The modules integrate the ADC, an ADC driver, a reference buffer, and an efficient power block, as well as critical passives to optimize performance, including the RC low-pass filter between the driver and the ADC. The result is a low-power, high-bandwidth module that eliminates many design challenges while offering improved performance over typical SAR ADCs. The modules also offer dynamic power scaling and flexible power down modes to further reduce power consumption. The ADAC 7980 and ADAC 7988 are ideal for automated test equipment, battery-powered instrumentation, communications, process control, and medical instruments.
Writing a simple blocking ADC driver. We can write a really simple ADC driver that is about the hardware layer. For example, we can create a simple functionate ADC sample that gets off the ADC hardware, and then stores all the results in a buffer that can then be accessed by the application. The buffer that stores the analog values doesn't necessarily need to store just a single value, but can store multiple values that could later be averaged or filtered based on the application need. The blocking version for the simple function might look something like the following. As you can see in this code, the while loop blocks execution until the ADC hardware has completed its conversion and then insert the values in the application buffer. Writing a simple no-blocking ADC driver, converting the blocking driver to no-blocking code is quite simple, but it will require changes to the higher level application code. For example, right now, if the application was to sample the sensors, a developer code. In the no-blocking version, a developer has to check the return value from ADC sample to see if the samples are complete and ready for use. This allows the samples to run in the background application code to continue running with the following updates to our driver code.
Hello, my name is Patrick Kuzior, and with me today is Applications Engineer Reem Malik. Reem, welcome.
Thanks, Patrick.
Reem, can you tell me about the AD8475?
Sure. The AD8475 is the industry's first fully differential funnel amplifier for driving precision analog-to-digital converters.
What is a funnel amplifier?
So, a common problem in motor control, process control, and instrumentation applications is that you have large input voltages up to plus minus 10 volts that need to be processed by single supply 3 volt or 5 volt analog to digital converters. Traditionally, this is accomplished through passive attenuation and many signal conditioning steps that require many costly precision components.
So if I understand this correctly, the AD8475, it's an integrated solution that funnels plus or minus 10 volts down to 5 volts and 3 volts?
Yes, exactly. The part simplifies the design of this critical interface between analog and digital by integrating these signal conditioning steps into one IC. The AD8475 attenuates large signals, does level translation, and drives differential input ADCs while running on the same single supply and reference voltage as the ADC itself. At the same time, it provides better performance and better precision than is possible using a discrete solution.
So the part eases design, speeds time to market, reduces bill of materials, and saves on board space. What else can you tell me about the part?
The AD8475 features two pin-selectable precision attenuating gains of 0.4 and 0.8. It has differential rail-to-rail outputs, and it has inputs that can accept voltages well above the supply rail. It has a combination of low noise at 10 nanovolts per root hertz, high speed at 100 megahertz, and low distortion while consuming only 15 milliwatts of power. This makes the AD8475 optimal for driving differential 18-bit ADCs up to 4 megasamples per second in industrial and instrumentation applications.
Thank you, Reem. And for more information on this product, please visit analog.com/AD8475.
And it has as conclusion, as we have seen, there are multiple ways to write in the ADC, and the implementation can be blocking or not blocking. Based on our needs, blocking drivers tend to be simpler and less complex than non-blocking drivers, but they can be inefficient. Non-blocking drivers allow our code to run while the driver works, but the application code still needs to shape and own the status, which in itself is inefficient in a pod implementation. Thanks for your attention.